Hello and welcome to the first episode about applying marketing mix modeling using Python. All right, so we're gonna do what we're going to cover today is we're gonna try to do a bridge of what we've done in the past using linear regression in Excel, doing all the exploration phase, create a simple model, and see how accurate it is. We're gonna do the same thing using Python. So the steps that we're gonna cover are what libraries we need to import and how to import them. We're gonna import our data frame and we're gonna see how. And let's see if all right, we're gonna see how. And then we're gonna show graphs and do some exploration analysis. We're gonna use ordinary least squares library or stats models library that has a function called ordinary least squares to do some statistical analysis. We're going to see what metrics we need to understand in order to validate our hypothesis and create an MMM project done well. Then we're going to use a linear regression function from scikit-learn, and then we're going to do some post-modeling analysis. So let's start importing libraries. We actually need only 4 or 5 libraries. It's going to be super easy. The first one is pandas. We need to have a way, libraries is a library used to manipulate data sets. It's super incredible, easy to use, and super powerful. So I'm going to do import pandas as PD, then import plotly.express as px. Plotly.express is a library that allows us to have interactive graphs in which we can zoom in, zoom out, and it's incredible. It's really incredible. Then we're gonna import stats models as SM, and then we're gonna do from scikit-learn.linear_model import linear regression, and from scikit-learn.model selection we're gonna import train_test split. And this function is used to do something that in data science is a must in order to validate your hypothesis really well. This function allows us to easily separate and divide into our data sets in 2 parts, in which we're going to use the first part to train our model, and then we're going to use the second part to validate our model. To validate how well it can predict. So let's let's run it. Perfect. Now let's define our data set. So we've done the first part. Let's import our data frame. Our data frame is df equal. We're going to use the function read CSV from pandas. So pd.read_CSV. Open parentheses, we're gonna copy the path from this CSV file, and then we're gonna rad.head. Right, let's describe. Let's see what comes out. All right. No, let's just run df. This is our data set and how pandas shows datasets basically, and we can see that we have a weekly aggregation as we had in the past episodes in Excel. We have 30 records. In these 30 records, we have sales, time frame, how much we spend on Facebook, how much we spent on TV, and how much we spent on radio. Now, we imported this df. What I'm going to want to see now is how they behaved over time in order to see if all the inputs over time are correlated in some way. So if they move up, also sales move up. That's what I want to find out. And we do that using Plotly Express. So coding wise, what we do is fig equal to px dot line, open parentheses. We define what's the data frame we need to take into consideration. Then the x-axis needs to be time, as we've seen here. And then in the y-axis, what I want is df.columns. So I want everything. I just want to see how everything is showing. I'm going to do fig.show, and it's going to show me everything. So here what we have is sales, right? So they have different dimensions. So this is really high. And what I want to see is, yeah, as we've seen in the past episode in Excel, this is Facebook, and when Facebook is rising, also sales rise with it. Let's see here. Yeah, Facebook rises, sales rises too. This is TV. TV seems a little correlated, but we can see that radio has positive spikes when sales have downward spikes. So they're not really correlated, I've seen. Let's check real quick if the Pearson correlation metrics. And Python and pandas have a really simple way to do it. It's just df.car, run it. As you can see, we have correlation between sales and Facebook, sales and TV, sales and radio. There is an incredibly low correlation between radio and sales. Okay, correlation between TV and sales, but really high correlation between Facebook and sales. That's good. Now, what we want to do is we want to do scatter plots. So what we do is we define a new fig equal, let's call it fig1, just to have some coherence across all the notebook. So we're going to do px.scatter, open parentheses. We're going to define df as a dataset. X is equal to Facebook. All right, we're gonna Facebook, and y is gonna be equal to sales. Fig1. Let's do something faster. So I'm gonna copy 3 times. I'm gonna call it fig1, fig2, fig3. We're gonna change this TV and radio, and let's show everything. Let's fig1 show, copy it 3 times, 2 and 3. Let's run it. All right, as we can see, sales and Facebook are really correlated. So if you see a trend, when the budget is invested is increasing, if we have a positive correlation, so the points are going up, it means that there is a clear correlation in here. Sales and TV are a little correlated. There are some, as you can see here, these are anomalies that made the correlation lower. They're not really good for all the regression, but it's whatever, we have it. And then we have all the rate investments that are really low correlated. We shouldn't put it inside. In order to validate our hypothesis, if we should insert our rate or not, we're going to use OLS, ordinal least square from stats models. I already inputted everything. We have inputs. We define Facebook, TV, and radio. We define X, which is our input variables, independent variables, is df inputs. Y is df sales. We add in the OLS stats models library a constant, because we know that when the variables are all input variables are all 0, we still have some positive conversions. Then we print results as SM OLS X epsilon and X dot fit, which is the function for ordinary squares in the stats models library, and then we print the summary. So run it, and in this case, we have some metrics and KPI we need to take for. This is, I think, one of the most important part for an entire marketing mix modeling project. We have the R-squared, which measures accuracy. So it basically tells you what is the percentage of variation in the input variables are describe the output variables, describe the variation in the output variables. We have the F statistics, which is a metric and a KPI that measures how statistically significant is the entire model. And it should be higher than 2 in order to be statistically significant. Now, let's measure here. We have the first column, so the dimension in here is constant, Facebook, TV, radio. So there are the input variables for our model. We see that we have an input coefficient for constant of 3.36, which if we compare it with our model on Excel, we have a 3.01, which is super similar, right? So we are here, and it's okay. Facebook is at 0.04, TV is at 0.18, and radio has a negative coefficient, which doesn't make sense. It doesn't exist an investment that drives negative sales. We now here have a standard error. So how much we think it can vary, how much this value can vary from all the historical data. And we can see, and actually this standard error is used to measure then p-value. And the p-value measures how statistically significant is the coefficient. So if the coefficient has a probability higher than 95% of happening, it's good. If not, if it has a p-value lower than 95%, but higher than 0.05, it's bad. As we can see, here we have most of our variables are lower than 0.05, which means that these three are statistically significant. Well, what is not statistically significant is radio. The confidence interval in here tells you what is the range in which your coefficient here could vary in a 95% confidence interval. And constant has a pretty wide range of values. Facebook has a pretty low range of values, same for TV, and radio is not statistically significant. Ergo, we should eliminate it. So what we do here, let's copy this code, let's paste in here, and we're going to remove radio. Let's see what happens to our model. Our model it decreases, the R-squared decreases a little bit from 0.8875 to 0.872. Perfect. F statistics increases, which is good. All the variables are statistically significant. They're all positive, which is good. And there's another thing that I want to mention, which is condition number. And a condition number is a variable, it's a KPI that measures what's the multicollinearity inside of our models. And what we want to have, because we have a linear regression, which is a function that describes it's something like this. I'm going to comment it. Epsilon is equal to beta1 x1 plus beta2 x2, etc., plus beta0, for example. We want to have all the inside axes independent and not collinear to other input variables. It would create some problems over time if there is high multicollinearity inside. So what we do here is we now define what's the best model. We're gonna run the train test split to divide our data set. So we do x train, y train, x test, y test equal to train test split. Let's run x epsilon. We're gonna do shuffle equal false. We don't want to shuffle our data. And test size, let's start with 0.2, right? Now, I'm not gonna run it because I want to find out. We're gonna divide our data set, and we're gonna use 80% for training and 20% for testing. I decided to not shuffle the data, which means I want this particular order, because in the long term it's gonna be useful for the ad stock. We don't want to shuffle the ad stock, but we're gonna cover it later. Anyway, so let's initiate our model. So we do model equal linear regression. Perfect. And we want to do model dot fit, open parenthesis, x train, y train. So it's gonna learn and train, basically. And then I want to print the score. I want to see what's the score, what's the R square for model.score x train, y train, comma, model.score x test, y test. Perfect. And so let's run it. We find a 90% R square in the training set and 38% in the test set, which is, it's not good. Let's see what happens if we increase the test size. So if we train the data set using a little more than 15 rows, records, let's see. They tend to converge a little bit. Let's try to find 0.5, for example. Yeah, it's way closer. Now it makes a lot of sense to have these two. Now, we train only on 50% and use the other 50% to test the data. Let's see what happens if I put 20% on test set and I want to shuffle the data. So I put true. And what happens is, in this case, in which we don't transform with add stock any function, and we don't transform anything, shuffling data is not something bad to do. Because what happens is, what the linear regression does, it measures the instant in the same week how many variation has been in the input, and measure what happened in the same record in the same week, what happened to the output. So if we shuffle the data, there's no seasonality, there's literally nothing that can impact negatively the linear regression. Because most of the times, what happens is the efficiency and the effectiveness of our advertising until this point are in one way, but after this point are another. Let's take, for example, if this here was April 2021, obviously the effectiveness of our Facebook ads or Google ads would be different in the previous period of April 2021 compared to the next period, because we obviously had a change on restriction cookie policies that affected all our advertising. So the dynamics change after that point. And what we want now is, in a simple linear regression, we want to first shuffle the data so we are more agnostic. We're not influenced to the changes over time. So let's do 20% of test set. We shuffle the data. Oh, wow, the test set, it's even more bigger than the training set, which is, let's do refresh it again. This doesn't make any sense. All right, still, obviously 20% is 6 records out of 30 records, obviously. So it tries to find what's the R square on that 6 records. And it find it, which is pretty good. They converge a little, and obviously there will be required more records in order to drive and do a regression analysis that's done well. Anyway, so what I want to do, I want to see the axis in this case. All right, so what we have here, we have a constant, and this constant does not make. Let's see. Well, let's see the coefficient. All right, so model.coef. We have 0. Let's see what. And I want to see x.columns. So we have constant, which is at 0 coefficient. So we don't take it as an input. We have Facebook, which has 0.049, and TV, which has 0.16. Let's see if it's different. 0.046, here 0.49. And here we have the coefficient. Let's see. And then we have 0.16, 0.16. All right, so they're really similar. Let's see the intercept. Model.intercept 3.03. In here is being 3.17. All right. So what we want to do now, let me change these two. X.columns. Perfect. So we know that the first coef is for constant, the second coef is for Facebook, and the third coef is for TV. Now, what I want to see now is let's drive and see what is the what's the prediction. All right. So we do df parenthesis prediction. So we add a new column, put it equal to model.predict, and put x in here. Now we want to see how the prediction, how accurate is the prediction. So we do fig equal to px dot line df x is equal to time, as always, and then epsilon is equal to, let's say, df dot columns. So to make it easier, so fig dot show, let's print it. I don't want Facebook, TV, and radio. I click on it. Look at that. So it's pretty good. It's pretty efficient, right? So it drives and can predict pretty well all the spikes, positive spikes and downward spikes, except some of them, which are here, which are here. My question is, how would it differ if we didn't shuffle it? So we put false, and we have a really low R square in the test set, 38%. The coefficient changed by a lot. Let's see what happens. If we do a prediction, we eliminate Facebook, TV, and radio. They're actually still, they're still pretty good. So, all right. There is more variance in here, because this would be probably test set. Test set will start here, and there is more variance. Let's see if I put 0.5. All right. The test set will start here, and it will predict pretty well, actually. It's not that bad. Let's see if we want to analyze how it is the CPO. So we have for Facebook, we have at 0.05. So we have Facebook is equal to 0.1 divided by 0.05. We have the CPO. So we need to divide the coefficient of our model. 1 divided by coefficient. We have the approximated CPO, which is considered constant. So if we run Facebook, we have a 20 euro or dollar CPO. If we run for TV, in which we have 0.12, TV is equal to 1 divided by 0.12. We run TV, we have an 8.333 CPO. So radio, it's not considered. And let's see how many model.intercept. It's 3.13, which is the number of sales we will get if we did not spend in any of these two channels. Now, obviously, we have to figure it out a way of doing diminishing returns and add stock on this graph on this project. But I want to stop right here for the moment because we covered a lot. It's almost half an hour of project, and I don't want to put too much stuff in the first step. Let me know in the comments if everything was clear so far. I try to be, obviously, as always, as clear as possible. And I want to check your feedback before doing the step 2 and implementing all the diminishing returns, add stock, and see how we can optimize budget using Python. All right. So thank you for staying with me this half an hour. See you in the next video. Bye.